All right, let's dive into something that's all around us all the time. It's the force that's literally holding you in your seat right now, the same one that keeps our planet from flying off into space. We're talking about the grand architect of the cosmos, gravity. It all boils down to one of the first questions we ever ask. It's so simple, but so profound. Why? Why does an apple, a ball, or anything at all always fall in the same direction? Why down?
And yeah, the classic image is Isaac Newton getting bonked on the head by an apple. It's a great story, that flash of inspiration. But the real genius here isn't just noticing a piece of fruit falling from a tree.
No, the real puzzle was this. If that same invisible force can pull an apple out of a tree, why can't it pull the moon out of the sky? Think about it. Why does one fall straight down while the other one just hangs up there? That's the mystery we're going to solve.
Some people have called it the universal glue, and honestly, that's a perfect way to put it. Without gravity, there's nothing to hold us together. We wouldn't be here. The Earth wouldn't be here. The entire solar system would just fly apart into nothing.
So to really get a grip on gravity, we actually have to rewind the clock, even before Newton. Our story really kicks off with a guy who had the guts to question 2,000 years of accepted wisdom. For literally centuries, everyone just went with what the ancient Greek philosopher Aristotle said. I mean, it makes sense, right? It feels intuitive. A bowling ball should fall faster than a feather. But then, around the year 1600, this Italian scientist, Galileo Galilei, said, you know what? Let's actually test that. So, the legend goes he climbs all the way up the Leaning Tower of Pisa. He's got two objects, a heavy one and a light one. The crowd's down below, totally expecting the heavy one to hit the ground first. He holds them out and lets go. And they hit the ground at the exact same time. Boom. Just like that, he proved that gravity pulls on everything equally. The only reason a feather floats down while a bowling ball plummets is because of air resistance getting in the way. If you did that same experiment in a vacuum, they'd fall perfectly side by side. So, Galileo showed us how things fall, but it took Isaac Newton to figure out why. And this is where that apple and the moon finally come together in one stunning universal law. See, Newton's big aha moment was realizing that the force yanking that apple to the ground was the exact same force reaching all the way out into space, grabbing onto the moon and pulling it toward Earth. The moon is falling. The trick is, it's also moving sideways so incredibly fast that it continuously misses the Earth. That path of falling and missing is what we call an orbit. It's the same physics that keeps our satellites and GPS working every single day. And Newton broke it all down into two beautifully simple rules. First, mass. The more stuff something is made of, the stronger its gravity. It's why you feel the pull of the Earth, but not the pull of, say, a basketball. Second, distance. Gravity gets weaker the farther you get from something. That's why the sun, which is unbelievably massive, doesn't just rip you right off the planet. Okay, so this leads us to one of the biggest misconceptions about going to space. If gravity is everywhere, pulling on everything, then why do we see astronauts just floating around like there's nothing there? Well, the answer is all about understanding the crucial difference between two little words that we tend to use interchangeably all the time: mass and weight. First up, mass. Mass is just the amount of stuff you're made of. All your atoms, your molecules, everything. That amount never ever changes. Your mass is the same on Earth as it is on the moon or Mars or floating in deep space. It's you. Now, weight is totally different. Weight is just the measurement of how hard gravity is pulling on your mass. Since the moon has way less mass than the Earth, its gravitational pull is much weaker, only about 1/6 as strong. So if you went to the moon, your mass would be exactly the same, but you would weigh only 1/6 of what you do here. And this gets to the heart of floating in space. Astronauts don't feel weightless because there's no gravity. Oh, there's plenty of gravity. They feel weightless because they are in a constant state of falling. They and the space station are falling toward Earth at the exact same rate, so there's nothing pushing back up on them to give them the feeling of weight. It's that stomach in your throat feeling you get for just a second at the top of a roller coaster drop. Now, imagine that feeling, but it just never stops. That's free fall. That's what it feels like to be in orbit. So, Newton's laws were amazing. I mean, they got us to the moon. But then, In the 20th century, a guy named Albert Einstein came along and showed us that gravity is actually something far, far stranger and way more beautiful than we ever thought possible.
Einstein's idea was completely mind-bending. He said, what if gravity isn't a force pulling things at all? What if instead, massive objects literally bend and warp the fabric of the universe itself, a four-dimensional sheet that he called space-time?
Here's the classic way to picture it. Imagine space-time is a huge, taut rubber sheet. Now, put a heavy bowling ball, let's say that's our sun, right in the middle. It creates a big dip, right? Now, if you roll a little marble, that's the Earth, past it, the marble doesn't get pulled by the bowling ball, it just follows the curve in the sheet. That, Einstein said, is gravity. It's just geometry.
Now, this probably sounds like something out of science fiction, and it was, until 1919. During a total solar eclipse, astronomers could suddenly see stars that were supposed to be hidden behind the sun. The sun's enormous mass was bending space-time so much that the light from those distant stars was actually curving around it to reach Earth. Einstein was right.
But here's the thing, even Einstein's masterpiece isn't the end of the story, not by a long shot. Today, physicists are staring down an even deeper, even more confusing mystery. And this is the biggest problem in physics today. Einstein's theory of gravity, general relativity, works perfectly for big things, planets, stars, galaxies, but it completely falls apart when you try to apply it to the super tiny, bizarre world of quantum mechanics. Our two best theories for describing the universe literally don't work together. So the holy grail right now is to find a theory of everything that can finally unite them.
So, from Aristotle's common sense to Newton's universal force to Einstein's warped reality, our journey to understand gravity has really been a journey to understand our place in the cosmos. It's the weakest force we know of, but it runs the whole show on the grandest scale. The only question left is, what other secrets is it waiting to tell us?